Hi there. Well, in this video we're going to look at a proof of the following limit, and we're going to use the squeezing theorem to prove this. Up until this point we've just kind of been using this fact that it equals 1 in other examples, but now we're actually going to prove this beyond a reasonable doubt. Okay, so first things first, let's go to a different screen and let's look at the following construction. What I've done is I've created a unit circle, and there's three objects that I've constructed on this unit circle. I have this great big triangle, I have this little green triangle, and then behind the green triangle is this yellow sector. Okay, and by construction, the way I've constructed it is the great big triangle contains the yellow sector contains the green triangle. Okay, so by construction, the area of the big triangle is bigger than the area of the sector, which is bigger than the area of the green triangle. Let's keep that logged in the back of our mind, and let's now get back to these pictures. Okay, you can see I've just kind of broken them up. This is going to represent the area of my great big triangle. This represents the area of my sector, and this represents the area of my green triangle. Okay, I've left the little yellow piece here just for comparison. Okay, so we can see that this area is bigger than this area, which is bigger than this area. So let's actually go out and find these different areas. Well, how do you find the area of a triangle? And the area of a triangle is simply base times height divided by 2. Well, what is the base of my big triangle? Let's make it look sort of like in the picture. Well, I guess that's good enough right there. Maybe it looks like that. The base of this great big triangle is going to be 1. Okay, because it's a unit circle, this is the ordered pair 1, 0. Okay, let's go back now, and this area right here is 1. Okay, well what's this height? We know this is a right angle right here. This is a right angle, so what's this height right here? Well, you'll notice that I have an unknown side, I have a known side, and then I have this angle. And what relates all three of those? And if you said tangent, you would be correct. The tangent of theta equals the opposite divided by the adjacent. Well, y over 1 is just y. So my height is actually just the tangent of theta. So what is the area of this triangle then? Well, it's going to be the base, which is 1, times the height, which is tangent, divided by 2. So the area of the great big triangle is the tangent of theta divided by 2. There it is. Well, what is the area of the green triangle? The area of the green triangle, let's just go back to the picture, and you'll notice that this base is also 1. But what is this height? What is this height right here? Okay, if you know it, great. If not, I'm going to explain it here real quickly. Okay, so we know that this base is 1. But what is this height right here? Okay, well, let's just go up to this picture. And if you think back to your trig class, this guy right here is, we'll call y. Since this is a unit circle, then the hypotenuse of this triangle is going to be 1. Well, I have 1, theta, and y. What relates all three of those? Sine does. So the sine of theta equals opposite over the hypotenuse. So really, this segment is just equal to sine. This is the sine of whatever that angle is, whatever this angle is right here. Okay, so what is the area of that green triangle then? Well, it's going to be its base, which is 1, times its height, which is sine, divided by 2. So that will just be the sine of theta divided by 2. There's the area of my green triangle. Okay, finally, what's the area of this yellow sector? Well, to find the area of a sector, you may or may not remember this from geometry, but let's get rid of some lines here, and I'll hopefully illustrate this for you. Oops, not that one. Okay, so if I have this yellow area and I'm interested in the area of that sector for any given theta, this theta could be anything, you can see that the area of that thing is simply a fraction of the area of the entire circle. Okay, well, what fraction is it? Right there. Looks like it's 1/4. Where did 1/4 come from? Well, what's 90 degrees divided by 360? And it would be 1/4. What fraction of the circle is that? It's going to be 1/2. Well, where did the 1/2 come from? It came from my angle, 180 degrees, divided by 360 degrees. That's my 1/2. Okay, or you could think of it in terms of radians. In terms of radians, it would be pi radians divided by 2 pi would be 1/2 as well. Well, we don't know what the angle is. Okay, so the multiplier that we're going to use is the angle theta divided by 2 pi. Okay, so what is the area of my original circle? Well, the radius was just 1, so the area of the circle is pi r squared, or pi. But that's the area of the whole circle, and we just want the area of the sector. So we multiply by the angle divided by 2 pi. Now, the pi's reduce, and I'm just left with theta over 2. So theta over 2 is the area of the sector of this circle. Okay, well, by construction, we know that that area is bigger than this area, which is bigger than this area. Okay, and you might be, if you haven't seen this before, you're probably a little bit confused as to how this relates to the original problem, but it's soon going to make sense. Okay, the next step might seem like a little bit of magic. You might be thinking, well, how in the world did you ever think to do that? And I got to admit that sometimes when proving things in math, creativity can certainly be your friend. So what I'm going to do is I'm actually going to multiply every term here by an object. And this object, or I should say a function, this function is the sine of theta over 2. How did I know that? Well, I kind of know where I need to be going, and this is going to allow me to get there. I'm going to multiply every term by that guy. And just to make sure that we can actually do that and maintain these relationships here, what if I had 2 and 4? Clearly 2 is smaller than 4. If I multiply everything by 3, I get 6 and 12. Well, that relationship is still maintained. It's still maintained. So this guy right here, we know this is a first quadrant angle here, so this is a positive value, so all these relationships are going to be maintained. That's just kind of a little aside. Well, if I multiply, you know what? I just realized that I made a mistake here. It's not sine of theta over 2, it's 2 over the sine of theta. That's what I want to multiply by. Sorry about that. Little brain freeze. If I now multiply this through the first function, the 2's reduce, I have the tangent of theta over the sine of theta. Okay? And the sine of the tangent of theta is really sine of theta over cosine of theta. I'm just rewriting this up here now. But instead of coming down here and dividing by this sign, I'm going to instead multiply by the reciprocal. And I'm just using the little known mathematical truism that dividing by something is the same as multiplying by its reciprocal. Notice that the signs drop out and I'm left with 1 over cosine. Okay, well, I should probably do this in a different color here so it doesn't get too messy. That was that. Okay, now let's go ahead and let's multiply those two together. You'll notice your 2's drop out and you're left with theta over the sine of theta. Now that looks familiar, doesn't it? It's not quite what we want, but it's starting to take shape a little bit. Okay, and then finally, sorry about that, didn't want to do that. The last one, if we multiply that, you'll notice that 2 over the sine of theta times sine over 2 is just 1. Okay, everything drops out, and it's just 1. Okay, so this relationship is maintained, and life would be really good if that were flipped. Okay, well, let's flip it. Well, I just can't flip this thing. I have to flip everything. But if I flip everything, the relationships change. Once again, just go to something that you know. If I have 1/2 and 1/4, okay, 1/2 is bigger, but if I flip 1/2, I get 2, and if I flip 1/4, I get 4. Well, the relationship changed. Okay, so let's go ahead and flip cosine. And I get, or 1 over cosine, I should say, and I get cosine. And this is going to be the sine of theta over theta. And when you flip 1, you just get 1. And these relationships are all flipped as well. Okay, well, there you have it. I have our function, sine of theta over theta. Oops. Sine of theta over theta, which is the function that I'm interested in. And it's sandwiched in between these two functions by construction. Okay, so now let's go ahead and let's look at the limit. The limit as theta goes to 0. This is the power of the squeezing theorem about ready to take hold here. What is this limit? We could just use direct substitution. This is a 0 here, not a theta. Okay, sorry. If I just plug 0 into here, I get back 1. Well, let's come over here to the other function, the upper function. Okay, and I get the limit. What's the limit of that? As theta goes to 0 of 1. Well, what's the limit as theta goes to 0 of any constant? It's just the constant. Okay, so even though I have no way of evaluating this limit by any analytical means that I've used up to this point, I have found two functions that are smaller than it and bigger than it, such that when they approach 0, when theta approaches 0 on those functions, those limits are 1. So what do we conclude? By the squeezing theorem, then, we can absolutely say beyond a reasonable doubt that the limit as theta goes to 0 of the sine of theta over theta, because he lives in between these two guys, we can say without a doubt that its limit is 1. I hope that made sense. Thanks for watching, and see you next time.